Section 2.2, Techniques for Computing Limits. So in the previous section, we introduced this definition of a limit, and we looked at some kind of basic techniques for evaluating limits, namely using tables of value and using pictures, using the graphs of functions to evaluate limits. In this section, we're going to look at some of these algebraic properties of limits, which are going to allow us to take a more kind of algebraic approach to evaluating these. And it's going to make life a lot easier. We're going to be able to solve more complex limits more efficiently. So getting into these properties, it turns out that limits are pretty friendly to work with. We have a whole bunch of properties that make taking the algebraic approach pretty straightforward. So if the limit as x approaches a of f of x and the limit as x approaches a of g of x exist, and k is a constant value, then we have the following properties. The sum property says that if we are taking the limit as x approaches a of the sum of two functions, this is going to be equal to the sum of the limits. So what this means is that we are allowed to take this type of limit and break it up into two separate limits. And the reason this is helpful is because we might be taking the limit of a big function, a whole bunch of stuff going on the inside here. But if there's any addition or subtraction, as we're going to see in a second, we can take that big complicated limit and split it into two or more smaller limits. So that's really helpful at evaluating these. Okay, so similarly, we have this difference formula where if we're taking the limit as x approaches a of f of x minus g of x, this is the same as the difference of the limits. Great, so those are our first two. The next one is the constant multiple rule. If we're taking a limit of a function that is being multiplied by any constant k, so a constant is just some number, right? Not a variable, some real number generally. We can just bring that constant multiple to the outside of the limit. So we can rewrite this as k times the limit as x approaches a of f of x. We have a product rule. It turns out that the limit of the products of a product is the same as the product of the limits. So I can rewrite this as the limit as x approaches a of f of x times, here maybe I'll group it like this, times the limit of g of x. We have a quotient rule. The limit of a quotient is the same as the quotient of the limits, with one little exception. I'll give you a second to guess what that exception might be. So the exception is we don't want our denominator to go to 0. Okay, if the limit of that denominator goes to 0, then we have a little bit of a problem. Okay, so I'll just say if the limit as x approaches a of g of x is not equal to 0. Because once we evaluate this, our output should just be a real number, and we can't have a denominator in the 0, or 0 in the denominator, excuse me. Okay, the power rule. This one allows us to, if we are taking the limit, and really it's like all this stuff is inside of this limit here, we are allowed to take that exponent and bring it on the outside of the limit. So this is the same as the limit as x approaches a of f of x all to the power of n. All right, and same kind of thing applies for fractional powers, with a little caveat. So remember, fractional powers, or rational exponents we sometimes call them, the number in the denominator generally corresponds to some kind of radical, right? Like remember, if we have 4 to the 1/2 power, that's the same as the square root of 4, which is equal to 2, of course. So if we have an even number in the denominator, there's a restriction on what we can put into the base, right? We can't take the square root of negative numbers. So for this property here, there's an assumption. So this only works if the limit as x approaches a of f of x is positive or 0, so greater than or equal to 0. So that gives us a nice little basket of properties that we can use to work with some of these limit problems that we're going to be evaluating in the next couple pages here. So before we move into some of these examples, I just want to point out one of the most basic, or the most basic kind of algebraic approach to evaluating limits. Limits of linear, polynomial, and rational functions can be found using direct substitution as long as the number c is in the domain of f. So the number c, that's just the value that x is approaching. So if we're looking at the limit as x approaches c of f of x, again, assuming that f of x is either linear, a polynomial, or a rational function, as long as c is in the domain of f, this is just going to be equal to f of c. So let's look at a few examples here. So this first one, we're looking at the limit as x approaches 1 of a rational function, x squared plus 3x plus 1 over x minus 2. So the first thing we should always try is direct substitution, because as long as this 1 is in the domain of this function, this limit is just going to be equal to this function evaluated at 1. So is 1 in the domain? Can we plug 1 into this function and get out a real number? Well, the only thing we have to really watch out for with these rational functions is, will the denominator go to 0 if we plug in 1, right? That's the big thing to watch out for. In this case, no, right? So this, we can direct substitute. So we are allowed to just plug in 1. So let's do that. 1 squared plus 3 times 1 plus 1 over 1 minus 2. And this simplifies. I think we get 5 in the numerator, and we get negative 1 in the denominator. So this limit is just equal to negative 5. Okay, nice and easy. So it's always worth checking to make sure that you can't just direct substitute before you start exploring other directions. Now for this next example, notice that we're looking at the exact same function, right? X squared plus 3x plus 1 over x minus 2. But in this case, we're looking at x approaching positive 2. Okay, so the only thing that's changing here is that a value. So is 2 in the domain? Can we get away with direct substitution again in this case? No, it turns out we can't, right? Because if we plug 2 into that denominator, we're going to get a 0. It's going to be undefined. Okay, so 2 is not in the domain of our function. Therefore, we're not going to get away with direct substitution. So the next line of defense, usually trying to simplify the function can be helpful, might be helpful. And with a rational function, generally simplifying looks like doing some factoring, seeing if we get any common factors in the numerator, denominator. That's usually worth a try. Can we factor this and simplify this at all? Well, looking at the denominator, that's totally factor. There's nothing I can do there. Looking at the numerator, is this going to factor nicely over the real numbers? Well, if it did, we would need to find two numbers that multiply to 1 and add to 3, right, using the diamond method. There are no two such numbers that do that. All right, so this doesn't really factor in such a way that's going to simplify it all. So I might have to take kind of a graphical approach here to look at this. Okay, so the function, if you go to graph it, and you all should have graphing calculators on hand. Those can be really, really helpful at quickly kind of assessing what type of function we're working with. But I'm just going to show you what this graph looks like. This has a vertical asymptote at +2. Okay, you probably could figured that out by saying that 2 gives us a 0 in the denominator. Okay, and this function also actually has a slant asymptote. So an asymptote that looks something like this. Okay, and the graph looks kind of like this. I'm just sketching it just so we can get an idea of what we're working with here. Okay. Great. So, and we happen to know that we have this ordered pair 1, -5. So ordered pair 1, -5, right? That's why we got -5 as the limit as x approaches 1. It's because it's continuous at that point. But at x equals 2, we have a vertical asymptote, and we can see that the behavior near that asymptote to the left of 2, it goes down to -infinity. To the right of 2, it goes up to +infinity. So this is a really extreme case of the left and right limit not being equal to one another, right? And what do we say when the left and right limit are not equal to one another? The two-sided limit does not exist. Okay, so I'll just make a little note of that. The left limit, so the limit as x approaches 2 from the left of the function, I'll just call it f of x for now, is equal to -infinity. The right limit as x approaches 2 from the right of f of x is equal to +infinity. Those are not equal to one another. So that's why I'll say that this limit does not exist. So D, N, E. Okay, and also, I took a graphical approach here. You also could have used your calculator to do a table of values approach, right? Plugging in some x values that were close to +2. So you could have put in 1.9, 1.99, 999. You could have gone from the other direction and put in 2.1, 2.01, 2.001, and you would have seen the same kind of thing. You would have seen numbers getting really, really large in the negative direction as you plug in those values. Those x values approaching 2 from the left, you would have gotten really large values, so you would have seen it going towards +infinity if you were plugging in 2.001 and so on. Okay, but from that, and also just our understanding of rational functions, we see that the limit does not exist there. Okay, let's do a few more. On page 4, let's explore some other techniques. So for the limit as x approaches 4 of x squared minus 4x over x squared minus 3x minus 4. So first thing I always try, can I direct substitute here? So if we plug 4 into the denominator, are we going to get a 0 down there, right? Because if we don't get a 0, then we can just direct substitute. But if you plug in 4 down there, you're going to get 4 squared, which is 16, minus 12 minus 4. Unfortunately, this is equal to 0. Okay, so 4 is not in the domain of the function, so we can't do direct substitution. All right, and like I suggested for this previous problem, the next thing I usually do is, can we factor? Okay, we might get lucky if we factor. So trying to factor this, let's see what happens. So the limit as x approaches 4 of, so the numerator factors pretty nicely. It's just, common factor of x. So x times x minus 4. And the denominator factors as well, doing a little diamond method or whatever works for you, I'm fine with. What two numbers multiply to negative 4, add to negative 3? Ooh, I think we get negative 4 and positive 1. So the denominator will factor to x minus 4 times x plus 1. All right, so having it in factored form is really illuminating because, check it out. There's an x minus 4 in the denominator. Hey, no wonder we got a 0 in the denominator, right? That's the factor that's responsible for that denominator going to 0 when we plug in positive 4. But good news. There's a common factor of x minus 4 in the numerator and in the denominator. So I can simplify this algebraically, right? That's a common factor. Let's cross those out, and we get the limit as x approaches 4 of x over x plus 1. I'm really happy to be looking at this right now, because what happens if I plug in positive 4? Do I get a 0 in the denominator anymore? No, I don't. That factor, that sort of problematic factor, went away, so I can now direct substitute. Right? I could not direct substitute in the very beginning, but I did a little work algebraically, and it turns out I can in this case. So I'm going to plug in 4. I get 4 in the numerator. I get 4 plus 1 in the denominator, or 4/5. And that will be my answer. So there's something interesting and important that's happening here that I want to explain graphically to you. So our original function was this. F of x equals x squared minus 4x over x squared, what was it? Minus 3x minus 4. And we were able to simplify this down to just x over x plus 1. So the graph of, how about this function first? This is a rational function. It's got a couple asymptotes. It's got an asymptote at -1. That's a vertical asymptote. It has a horizontal asymptote at y equals positive 1. And the graph looks like this. Just a rough sketch. All right. So maybe I'll call this g of x. Okay. And then f of x looks exactly the same with one little exception. So remember, we saw that, when we tried to plug in positive 4 into the original function, we got a 0 in the denominator, indicating that 4 is not in the domain of the function. So it turns out that the graph of f looks exactly the same as this one, right? So it's the same shape, everything is the same. The only difference is that at x equals 4, let's say it's right here, there is a hole in the graph. Okay, the graph of g of x does not have that hole in the graph there. but f of x does. Okay, so we call this a hole. Okay, so this is a hole particularly at the ordered pair 4/4. So here's what's really interesting about this problem is at this point in our work here, we made this step where we canceled out x minus 4 in the numerator and denominator, and we put an equal sign here, right? And then just rewrote the limit again without those two factors. However, it turns out that without the limit sign, x times x minus 4 over x minus 4 times x plus 1, it turns out that without the limit sign, this is not equal to x over x plus 1, right? Because we see that graphically they're different graphs, right? They're pretty much the same, except this one has a hole in the graph at x equals 4. So why is it that these two limits, like there's an equality here if there's a limit symbol in front of it, but there is not an equality here if there isn't the limit symbol? Why is that? Remember, the limit does not care what's happening at the x value, x equals 4. It only cares what's happening to the function when we input values very, very close to 4 on the left and the right. So that is why we can have a limit symbol here, right? Because the only thing that changes when we cancel out the factor x minus 4 is the behavior of the graph at x equals 4, which the limit does not mind at all. Okay, so just kind of an interesting thing I wanted to point out here. But now going forward, generally when we see this kind of simplification happening where a factor, x minus 4, cancels out in the numerator and denominator, what that means graphically is that there's a hole in the graph. Okay, and we can generally get away with evaluating the limit in spite of that hole. Okay, so that gives us kind of one of our first big, important, useful techniques for evaluating limits. Sometimes I call this the simplify and cancel, or simplify and then direct substitute approach. Let's keep going. We've got another example here. So this example, we are looking at the limit as x approaches 9 of the square root of x minus 3 over x minus 9. Okay, so like always, I'll try to direct substitute. Am I allowed to plug 9 directly into this? No, I'm going to get a 0 in the denominator if I do that, so on to plan B. What else can I do here? You might think about trying to factor. It turns out you can get creative and factor this denominator, but I wouldn't necessarily recommend that approach because we have a nicer one, or one that's a little more intuitive, I think. So in the numerator, we have square root of x minus 3. So you might remember from your intermediate algebra class, we can simplify expressions or like rational expressions involving square roots or sums and differences involving square roots using this thing called the conjugate. So the conjugate is where we take this expression here, but we just change the sign of one of the terms. So what I'm going to do is I'm going to multiply top and bottom by the conjugate. Specifically, I'm going to multiply top and bottom by the square root of x plus 3. So see how I'm just changing the sign of the 3 from negative to positive? All right, so this technique, this is called multiply by the conjugate. And this is something that's worth trying when we have this kind of expression in the numerator or denominator. Let's see what happens. So to multiply these together, In the numerator, I'm going to, so fraction multiplication, you just multiply the numerators together, multiply the denominators together straight across. So multiplying the numerator, I am going to FOIL this out, or if you do the box method or whatever, some people like this box method where we'll multiply square root of x minus 3 times square root of x plus 3. So root x times root x just gives us x. Then we have negative 3 root x. Then we have positive 3 root x. And then negative 3 times positive 3 is going to be negative 9. All right, so that's why in the numerator I get x minus 3 root x plus 3 root x over, minus 9 over. So in the denominator, I'm actually not going to multiply this out yet because remember, the reason we were able to evaluate this previous limit is because we had that problematic factor x minus 4 and we were able to cancel it out, right? We want to make that problematic factor go away. So when I'm looking at simplifying this and multiplying this out, I don't want to multiply out the x minus 9 and the root x plus 3 because I'm hoping to have that cancel out, right? That's kind of the only way I'll be able to evaluate this limit by direct substitution. So let's leave it in factored form for now. Because I think something kind of nice is going to happen here. What happens to our numerator? Well, we have a negative 3 root x and a positive 3 root x. Those are going to add together to become 0. So we're just left with x minus 9 in the numerator. And down here we've got x minus 9 times root x plus 3. So it looks like we're getting lucky here. The x minus 9s, that common factor will cancel out. We'll just be left with the limit as x approaches 9 of 1 over the square root of x plus 3. Okay, remember that root x plus 3 is in the denominator. Sometimes I see people accidentally just write this, right? Like forget that, that's in the denominator. No. Keep that down there. It's just going to be under 1. Can we now evaluate this by direct substitution? Yes, we can. Let's plug that 9 in. We're going to get 1 over the square root of 9 plus 3. Simplifies to 1 over 3 plus 3. Our answer is 1/6. Great. So just another common technique, particularly if you see sums or differences involving square roots in rational functions, this can be worth trying if things aren't factoring and you can't direct substitute. Using the conjugate to simplify can work out. Okay, let's see this last example in this little section. The limit as x goes to 0 of 1 over x minus 1 over x squared plus x. Okay, well, we're taking the limit as x goes to 0. Can I direct substitute into either of these? No. That's going to go to 1 over 0. That'll be undefined. This one as well. If I plug in 0 for x, I'm going to get 1 over 0. So neither of those can be evaluated by direct substitution. You might be thinking, oh, there's a difference. I can break this into 2 separate limits, right? Sorry, this probably should have grouping symbols. We're taking the limit of this whole expression here. You might want to try to split that up into 2 separate limits, but it turns out that doesn't really get us any closer. What else can we try here? Well, we have a difference of two fractions here, two rational functions. We could try to combine these and see what happens. Like, sometimes we just have to try stuff, right? Just try things and see if we can get something to work. So maybe just combining these, because I can get common denominators. You know what, let me write in one more step here. Let me factor, right? Because this denominator of the second fraction factors to x times x plus 1. We can see that there's this common factor of x between these two denominators. So in order to combine, to add these two, or sorry, subtract these two fractions, I can just multiply top and bottom of this first fraction by the missing factor, which is x plus 1. Okay, so doing that will give me common denominators. So I'll have the limit as x approaches 0 of now x plus 1 over x times x plus 1 minus 1 over x times x plus 1. So we have common denominators. We can now just subtract the numerators. So we'll have x plus 1 minus 1 in the numerator, and then x times x plus 1 in the denominator, right? And then plus 1 minus 1, that just becomes a 0. So we have this. So what do we think? Do we like what we see? What was the problematic factor here that was causing those denominators to go to 0? Well, it was just the factor of x. And check it out, we got that common factor of x in the numerator and denominator. So those cancel out, or they make a big 1. And now we just have the limit as x approaches 0 of 1 over x plus 1. I can direct substitute in 0, and I'm just going to get 1 over 1. So the answer here, this limit is just equal to 1. Okay, good. So notice that in each of these last three examples, they all kind of ended the same way, where there was this problematic factor that was making it so we couldn't direct substitute. We did some algebra and it canceled out. It turns out in each of these cases, it was like this first picture we were looking at, where it was a hole in the graph that was making it so that we could not evaluate the limit. But in the end, you know, looking back to this first picture, if it's just a hole in the graph, but we still have, you know, the left limit and the right limit kind of lining up in that way, like they're going to the same number, as we can see in this picture, the limit will exist. So in each of these examples, and you could use your graphing calculator to confirm this, we just have holes in the graph at each of these values. Like for this second function, it turns out we have a hole in the graph at the ordered pair 9, 1/6, right? And in the third example, we have a hole at the ordered pair 0, 1. All right, so you can graph each of these to verify this, but this is why the limit ends up existing. We still have the left and right limits equal to one another, and we can confirm that visually looking at the graph. There's just that hole that was preventing us from direct substituting in the first step. Okay, so you'll have some opportunities on homework to practice these techniques, but these are very big, useful techniques. You'll see them all over the place. So yeah, good luck with those on the homework. Let me know if you have questions. I can always help out in office hours, or you could send me a message through Canvas if you need help. Okay, let's look at some one-sided limits. So we saw an example in the previous section where we had a piecewise defined function. We ended up graphing it, and we used the graph to evaluate the limit. So we can also do this by substituting. But it's helpful to think about the graph. Like, I'm a pretty visual person, so generally, even if I don't need the graph, I'm kind of thinking about it. What this graph looks like, or just the really important thing to acknowledge here, is that this is a piecewise defined function, and the transition from this quadratic function to this linear function occurs at x equals 1. All right, so at x equals 1, there's going to be the switch from the quadratic function to the linear function. And we are looking at the limit as x approaches 1 in this case. So that just kind of implies this is not going to be a boring example. We're going to have to be on our toes, and we're going to have to pay attention to the left and right limits individually to make sure that this two-sided limit exists, or find out that it doesn't exist. So let's look at each of these. So how about we start with the left limit? So the limit as x approaches 1 from the left of f of x. So we talked about this in the last section. Since we're looking, in this case, at the limit as x approaches 1 from the left-hand side, if we were doing a table of values thing, this would be where we're plugging in like 0.9 and 0.99 and so on. So notice that every number that we're going to plug in order to evaluate this left limit is going to be a number which is less than 1. So this means that we would be plugging into this quadratic function here. So that means that when I'm evaluating this limit, I don't really have to think about the whole piecewise function. Really, I can just think about the part that's relevant to this left limit at x equals 1. So, sorry, let me get this out of the way. Really, I can look at this as the limit as x approaches 1 from the left of specifically x squared plus 1. All right, and it turns out if we're looking at this function, this is defined, 1 is in the domain of this quadratic function. I can just direct substitute. So this is just going to be equal to 1 squared plus 1, which equals 2. Great. There's our left limit. Let's look at the right limit. And using the same kind of reasoning that we just did with the left limit, since we're picking values, like if we're using a table of values, we're plugging in values that are to the right of 1, so larger than 1. That means that really I'm just going to be plugging into that linear function, 2x. Okay, 2x is linear, 1 is in the domain. So I can just direct substitute. So this is going to be equal to 2 times 1, which is also equal to 2. Notice that the left and right limit are equal to each other in this case. So it turns out that the two-sided limit exists. Okay. So the left limit is equal to the right limit. Therefore, the two-sided limit exists. So the limit as x approaches 1 of f of x. So I'm not putting a plus or minus sign up here because I'm talking about the two-sided limit. This exists and it is equal to positive 2. All right, and I kind of delayed talking about the graphs, but let's do the graphs real quick. How about I graph the left branch in blue and then the right branch in purple? So this is a quadratic function, just the parent shifted up by 1 unit. So it'll look like this. Okay, and I stop the graph at x equals 1 because at that point, that's where we switch to the linear function. That's just the graph of a line. It has a slope of 2, y-intercept of 0. So this graph looks like that, linear function going in that direction. And I'm going to draw a purple dot right there, just because if we plug in x equals 1, technically we're plugging it into that linear function there. But it turns out the linear function and the quadratic function both output 2 at x equals 1. So they line up, and now we can see visually, there's the left limit and the right limit. And we can see graphically, visually, they're both going to the same number. So this is what it looks like when the limit exists. Just kind of confirming what we found algebraically. All right. So that brings us to the end of the section. So with these problems on the homework, they all look a little different. There is some trial and error involved. You'll have to play around with them. But we learned quite a few really important techniques here. The goal is to not rely on tables of values and graphs, because these are not really bulletproof methods for evaluating limits, right? We can't know, like, we could plug in 1.99999, but we don't know for sure what's happening, right? We're just kind of guessing. Like, we're not a infinite computer that can plug in every number that's approaching 2 from the left-hand side, right? So it's not totally bulletproof to do it using these methods. The goal is to evaluate these algebraically whenever possible. Okay, so for the homework problems from section 2.2, you want to be relying on these techniques more than those earlier ones. But have fun with these. Let me know if you have questions, and I will see you in the next section where we're looking at infinite limits.